Hello. So some of these examples we might get to in class. These are rotation examples. I wasn't sure and I wanted to make the video ahead of time. Anyways, so here we are. So there are a bunch of examples. I think there's 5 I'm going to do right now. 6, 5 or 6. I don't remember. That we're going to do in this video. And so again, some of them you may have already seen before, so don't feel too bad about, skip ahead if you need to. But you probably haven't seen all of them. All right, so first one, start out pretty simple. Phonograph starts from rest, starts to smooth angular acceleration of 0.4 radians per second. Top speed is 3 radians per second. How far will the record spin before the music can start being played? Okay, so this is just a classic kinematics problem. I've got initial angular velocity of 0, it's at rest. Final angular velocity of 3. And, it's got to be an alpha. And my angular acceleration of 0.4. Alright, and I'm looking for displacement, which is theta. So in order to do that, I need to use a kinematics equation. This is the omega final squared equals omega initial squared plus 2 alpha theta. Right? And we just plug in here. 0 equals, nope, not 0. 9 equals 0 plus 0.8 theta. Theta is 11.25 radians. Okay, pretty straightforward. Try a little bit trickier here. So I went from pretty simple to this is almost needlessly complicated. Okay. All right, so we've got a bike wheel, and we've got a bunch of radiuses of the wheel and the sprocket. The sprocket's the thing the chain attaches to. It's like the little spiky thing. And I want to know if you're biking, if you're biking at 10 meters per second, what is the speed at which your feet must move? So if you're, okay. So the first thing to understand here is that if we're biking, right, then the speed of the wheel, the tangential speed, v tangential of the wheel is equal to 10. That's the 10 meters per second. What that means is that then I can get for that omega of the wheel, right? Because we want to think about this. V equals omega r, right? So with that, I can get the omega of the wheel is 25 radians per second. Now, the wheel sprocket, right, that is going to have the same omega as the wheel. And that's because, right, they're physically attached, right? So every time the wheel rotates one time, the sprocket also rotates one time, right? So that is going to be also 25. And from that, we can get the v tangential of the wheel sprocket, okay? And again, using v equals omega r, it's 25 times 0.05, which is 1.25 meters per second. Now, how does that help us? Well, remember that if you're looking at a bike, right, we've got the back sprocket and the pedal sprocket, right, and they're attached by a chain. And so that chain is moving at the same speed everywhere along it. So the tangential of the wheel sprocket is the same as the tangential of the pedal sprocket. That's 1.25. And from there, we can get the omega of the pedal sprocket, which is 1.25 divided by the 0.08, 15.63. And guess what? The omega of the pedal sprocket is the same as the omega of the pedal, right? And I can get v tangential of the pedal from that. And it ends up being 3.13 meters per second. So the speed of your feet, in order to go 10 meters per second horizontally, the speed of your feet has to be 3.13 meters per second. Okay. All right. Now we're getting to a little moment of inertia. So this is a pickaxe, and if you know what a pickaxe looks like, I'm thinking of like the very traditional classic one. It's like a wooden pole, and then at the top there's like the curved axe part. And basically what we're saying is this is 1 meter. Okay. So we want to swing it by someone with 1 meter long arms. Okay. So essentially, the center, the axis, is here. It's being swung around somebody's body here, right? So we've got an arm, right hand. That's a terrible. That's a disturbing hand. Let's get rid of that. Okay. But we've got someone's arm, right, attached to it. We got the hand, right? We got the hand attached to it, and we got the arm coming out like that. Still kind of disturbing, but less disturbing. So, and this is also 1 meter. So, when you do the eye, it's going to be the eye of the pole, plus eye of the, I don't know, the metal thing, the blade. We'll call it blade. Okay. Eye of the pole is made up of I center of mass plus I offset, right? Talked about this offset thing, which is for a pole, it's 1/12 ml squared plus the offset, which is m r squared. So what is r? The center of mass of the pole is here. It is rotating around a point 1.5 meters away from that. Okay, so this is 1/12 times 2 times 1 squared plus 2 times 1.5 squared. This is 1/6 plus, and this whole thing is 4.5. And that's some nasty number like 4.67. Then we have the eye of the blade. Now the blade, this is again an approximation here, but the blade is all the metal is about the same distance from the center, right? If we like draw that line and that line, they're both about 2 meters. And so since all of the metal is 2 meters away, when we do that summation, right, we don't need to, it's all has the same R. So this is really for the eye of the blade. Right, it's the same thing as the hoop thing, where all the parts of the hoop are the same distance from the center. Well, eye of the blade is all that distance away, so it is going to be a mass of 3 times 2 meters squared. This is going to be 12. So I total is going to be 16.67. Okay. All right, another one. Got a large pendulum. It's made out of a steel rod. This is 0.8 meters long. And we got this little bob at the end here, which has a radius of 0.05 meters. And it is, at the moment, 30 degrees from the thing. And I want to know what the angular acceleration is. Now, we know that torque net equals not MA, I alpha. So I need to know what I is, and I need to know what torque net is to get alpha. So, first thing I equals I rod plus I sphere. That's going to be equal to I rod, which is, let's say I rod is I center of mass plus I offset, which is 1/12 ml squared, plus the offset, right? It's being drawn in one end, so the offset is it's our offset, but that is 1/12 times 3 times 0.8 squared plus 3 times 0.4 squared, right? Because it's offset half of its length. And that comes out to be 0.64. And then I sphere is equal to I center of mass plus I offset. For the I center of mass, it's a sphere, so it's 2/5. We assume it's full, it doesn't say hollow. 2/5 m r squared plus mr squared. And little r again is the offset. So this is 2/5 times 2 times 0.05 squared plus 2 times the offset is 0.85. It's not 0.8 because, right, that's where the edge of the sphere is. We want to go to the center. The center is 0.85 away. And that comes out to be 12. That's not 0.64. That was a lie. That first part of that's 0.64. It's actually 1/3 ml squared. Oh yeah, okay, yeah. No, it is 0.64. I'm crazy. It is 0.6. I'm sorry. Second guessing myself. It's 0.64, and this is 2.17. Okay, so got that. So total I is those two added together. It's 2.81. Now I need the torque. So look at the torque. I need to look at the forces on this. On the rod, we got the force. The both main forces here are gravity, and gravity acts at the center of mass. So I got Fg, and I have Fg, right? And it's R cross F. So the radius of this Fg is 0.4, and the radius of the other Fg is 0.85. So torque net equals R cross Fg. We'll call it the rod, plus R sphere cross Fg sphere. R rod is 0.4 times 3 times 9.8, and this is sine of 30, right? Because we want the angle between this and the radial. The radial vector is this vector right here, and that theta right there is what we're looking for. And this is going to be plus 0.85, which is the radius, times 2 times 9.8 times sine 30. And my total torque comes out to be 16.4. So to find alpha, it is just going to be 16.4 over 2.81, which is 5.84. Okay, radians per second squared. I should take it. That's the end of the first video here. So stop recording.